Great. So hello, everyone. Welcome to this week's AFMS seminar. It's my pleasure to introduce our seminar speaker today, Professor Kilian Oberleithner from TU Berlin. So that's the Technical University of Berlin. So he is the head of Laboratory for Flow Instabilities and Dynamics. Kilian completed his PhD in 2012, and at some point he spent a bit of time as a postdoc at Monash University before returning to Berlin in 2014. His research interests include reacting and non-reacting turbulent shear flows, and in particular using linear stability theory and data-driven low-order modelling to bridge fundamental and applied research. And he's going to be talking about some of this research today. So please take it away, Kilian.
Thank you, Kat. So welcome everybody to my seminar talk on instabilities and coherent structures in swirling flows and their relevance for thermoacoustics. So what are going to be the topics today? I will spend quite a lot of time on introducing the problem. So I will explain to you briefly the concept of a swirling flow, and then the methodology of coherent structure identification and modeling that we use. And I will also introduce you to Swirl Combustion thermoacoustics, because I think this is something you need for understanding the results, which I will then explain to you. And there we will talk about the impact of as I said on the title, the impact of the instabilities on thermoacoustics. And in particular, we focus on Kelvin-Helmholtz type instability, inertial waves, and helical global modes. So just to give you a very brief introduction here. So swirling flows are used in many different technical and natural flow applications. For instance, the Francis hydro turbine, gas turbines on delta wings, dust separators, wind turbines, and tornadoes. So in my group, we're working on the problem of Francis turbines, hydro turbines, and gas turbines, as well as a little bit on the wake of turbines. And we have also some collaboration with people working on tornadoes. So we are in touch with some of these applications here. So what is a swirling flow? You can think of a very simple experiment here where you have a water tank and you suck the water out of this tank, drive it through a pump, and then you drive the water through a honeycomb, and then you start rotating that honeycomb. And of course, this imposes some rotational motion onto your flow. And then you pass this flow through this contraction into this water tank. And if you take measurements at the streamwise position shortly downstream of the nozzle, you would get profiles like this. So the axial velocity profile is basically top head profile. So it's very similar to a non-swirling jet, except that you have a little bit of an overshoot at the jet center line. More interesting is your swirl component or your azimuthal component. So this consists of a region in the jet center, which is where you have a linear relation of your azimuthal component. So this is a solid body rotation, then you reach a maximum, and then your azimuthal velocity decay. So you have an azimuthal shear layer further outside. And then, of course, the swirl profile changes when you swirl the rotation rate of your motor, so you have different swirl intensities. Now, if you imagine taking flow visualizations shortly downstream of that contraction and you run this tank at very low Reynolds number, you can get images like this. So here at the top left, you have a non-swirling flow, so classic laminar axisymmetric jet with some roll-up of Kelvin-Helmholtz type instabilities. And then as you increase the swirl, the flow becomes more and more complex. You may identify here some helical modes. So you get some dominance of helical instabilities. And then what is most striking is that at some point when you increase the swirl high enough, you get some reverse flow here on the jet center. So you can see this here maybe in this image here, and if you increase the swirl number even more, you get a strong recirculation bubble on the jet center line, and you see that you have the roll up of the shear layer outside and inside. Okay, and this feature of vortex breakdown is going to be very important today. So if we look at the highest swirl number case, and we turn this image from top to bottom now, and we increase the Reynolds number to get a fully turbulent flow, you may identify similar features. So you still have a recirculation zone here in the center, and you have the roll-up of coherent structures in the inner and outer shear layer. And if you take data, so if you measure this flow or do numerical simulation and take the time average, it may look like this. So basically you have this very pronounced feature of a recirculation bubble here in the center. You have a stagnation point upstream of that bubble. You have the swirling flow that is winding around this bubble. And you have an inner shear layer, which is this blue line here, and an outer shear layer, which is this red line here. Okay, so this is basically the vortex breakdown state and the flow configuration that we are mainly looking at today. So what are the main instabilities, hydrodynamic instabilities that can occur in such a flow? So you have your breakdown state, and upstream of that state, you somewhere have a velocity profile that may look like this. So the blue is the axial velocity profile, and the red is your swirl velocity profile. So one thing which you can experience are inertial waves. So these are hydrodynamic waves that arise due to the Coriolis forces, and these waves typically, these waves are existing in the solid body rotation of your swirl profile, so in the inner region of your jet. Then you can have a centrifugal instability, which is driven by the centrifugal forces, and this type of instability arises in the outer region of your flow in the azimuthal shear layer. And then you can have, of course, Kelvin-Helmholtz type instability, which is driven by the axial shear, which you already saw on the flow visualization pictures. And it's driven by the axial shear, and of course is most dominant somewhere where you have a strong gradient of the axial velocity profile. And then what happens as well is that you can have global modes, and these modes are typical helically, or they're always helically. So the most prominent one is the single helical azimuthal mode with the mode number m=1, as shown in this quite classic picture here. Okay, so these are the 4 most important instabilities that can occur here. So before we come now to the combustion topic, I will briefly introduce you to the methodology that we are using. So I will keep this very brief, and there have been other seminar talks already that use similar methodologies who explained this quite in detail. So basically we're combining a data-driven and a physics-based approach here. So the data-driven approach is based on flow snapshots that we either get from experimental measurements like PAV or numerical simulations like LES. And then the first step is to exploit some symmetries. So if you know already your coherent structure has a certain azimuthal wave number, for instance, you can impose this as a preconditioner onto your data. And then what we typically do is we do a PUD or a spectral PUD where we decompose our fluctuating field into some time coefficients and spatial modes. And we use basically 2 versions of this approach here. The one we term frequency domain SPUD, which has also been reviewed very nicely by Town et al. And this methodology, which is basically a frequency decomposition of your data and then a PUD analysis, is very suitable for the broadband dynamics if you have broadband dynamics, and it gives you frequency ranked PUD modes. And the other version is what we call the time domain SPUD, which was introduced by co-worker Siba et al. And this one is basically that you take your correlation matrix and you put a filter operation on your correlation matrix, and then you do a PUD afterwards. And this methodology is very suitable for sparse and transient dynamics, and it's very powerful in discarding the broadband dynamics from your sparse dynamics. The physics-based approach obviously is based on stability analysis, and we apply this analysis to the mean fields. These mean fields you also need to have from either numerical simulation or experiments. And we impose classic modal ansatz, which also exploits some symmetries of your mean flow. And then we plug these answers into our governing equations, and then we linearize those equations with respect to this perturbation here. And we mostly do this for the momentum and mass equations, but there are also some cases where we use the energy and species transport equations, and this is particularly important for the reacting flow cases. And then if you have your linearized operator, you can do different types of analysis. You can do a resolvent or analysis, a global resolvent analysis, or a local spatial stability analysis, which is most suitable for amplifier flows and flows that are forced, either stochastically forced or harmonically forced. And then you can do, of course, a global eigenmode analysis, or as a local spatial temporal stability analysis to work out the global modes, which is most suitable for oscillator flows and self-excited instabilities. So I wanted to have this all on one slide to just briefly make clear that there are some connections between these two worlds here. So the frequency domain SPOD combines very nicely with the resolvent type analysis or local spatial stability analysis, while the time domain SPOD combines really nicely with the global mode analysis. However, if we're dealing with turbulent flows and we're applying our linearized analysis on mean fields, there's of course the problem of turbulent closure, and I will just briefly show you the equations and show you the closure problems, but I will not go too deep into that topic. Again, there were already some other talks which went a bit more detailed into this. So basically how we set up the problem is we're using a triple decomposition. So we are decomposing our flow variables, which can be velocity, pressure, density, a concentration field, or temperature, and we decompose this into a mean, a periodic or coherent part, and a remaining part. And then we plot this in our governing equations, which are the continuity, the momentum, the species transport, and energy equations. And you can see here in red the terms that are unknown or for which we need some additional equations. These are the coherent fluctuations of Reynolds stresses and coherent fluctuations of turbulent transport of our concentration field C and turbulent transport of our turbulent temperature fluctuation. You can also see here in gray there are some additional terms which come into the equations when you have some reaction model or some flame model. This is something we are also working on, but I'm not going to talk about this today. So to close these equations here, as I said, we need some additional equations, and we use a very simple approach here. We use the eddy viscosity hypothesis and gradient diffusion hypothesis to close this problem. And of course, this leaves you with the unknown eddy viscosity and turbulent diffusion coefficients. And those we typically calibrate to our data that we already have in order to get our mean fields. Okay, so this is in brief our approach here, how to close this problem here. All right. So I'm coming to the end of my introductional chapter soon, and I will reach my research question. So next, I will introduce you to swirl combustion. And this is also something you need to know to understand the results afterwards. So why do we actually use swirling flows for combustion? Well, here you see a picture of a gas turbine. And inside this little chamber here, you burn your fuel, and then you run a turbine downstream of that chamber. So the big challenge here is that you have very high velocities in this combustion chamber, which are much higher than your actual burning velocity of your fuel mixture. So in order to not have the flame move downstream into your turbine, you need to have some sort of flame stabilization. So you need to have a region in the flow where you have low flow velocities so that the flame will stabilize in that region. And one possibility to do this is by using swirling flows. So here you see a picture of a swirling flame inside a combustion chamber. Now the flow comes from the bottom to the top. So there's a strongly swirling flow going into the chamber, and then you have this V-shaped type of fully premixed turbulent flame. And if you look at some PIV measurements in such a combustion chamber, they look like this. And what you see is a very strong recirculation or reverse flow region on the center of your flow, and an annular swirling flow going around this recirculation zone. And then, of course, you have some very strong shear layers. This inner shear layer is where our flame is stabilizing. Okay, so we are using vortex breakdown in order to have an aerodynamic flame stabilization. However, as I told you, there are a couple of instabilities, hydrodynamic instabilities, that become important for this type of flow, and this may affect the combustion process. But before we come to this, I need to introduce you also to the problem of thermoacoustics. So what are thermoacoustics? So in very basic words, it is a coupling of the acoustics of your combustion chamber with your flame, with the heat release of the flame. And if this coupling is constructive, you get very strong pressure oscillations, you get a resonance of the entire combustion system, and that is very harmful to the combustor, and you cannot run the gas turbine at such an operating condition. So you definitely need to take care of this problem. So what is happening in the, or how is the thermoacoustic oscillation actually occurring? So basically, if you imagine your combustion chamber and you have a flame in there, and this flame is somehow perturbed, let's say due to turbulence, you get some heat release fluctuations, and this Q here stands for the global heat release fluctuation. So the heat release fluctuation is integrated over the entire flame. This global heat release rate fluctuations then induces an acoustic wave. So your flame is basically an acoustic source, and these acoustic waves are reflected by the combustor or the combustion chamber, and maybe feed back into the flow and may couple to heat release. Okay, so there is a coupling between our acoustic field and our flame dynamics, or we also call this the response of the flame to acoustic perturbations. And this coupling is a very important ingredient to close the feedback loop leading to thermoacoustics, and this coupling is represented by a so-called flame transfer function. So this flame transfer function relates the heat release to the acoustic velocity fluctuations and in the frequency space. And this flame transfer function is a very important ingredient that has to be known in order to predict the instability of the entire combustion system. So finally, we now come to the research question here. So what we are trying to understand is how are hydrodynamic instabilities affecting this flame transfer function? How is it affecting the response of the flame to acoustic perturbations? And at the beginning, I introduced you to a couple of instabilities that are important in swirling flows. And now we're trying to understand how this is connected to the flame response. So basically, you have the Kilian-Helmholtz type instability. And of course, the Kilian-Helmholtz type instability is receptive to acoustic perturbations, and you have this roll-up of the shear layers, and this again causes a roll-up of your flame surface, and that again causes heat release. So there is a potential coupling here. And then second, you have the inertial waves, and these inertial waves, or in combustion community, we call them swirl fluctuations. They arise due to an impingement of an acoustic wave onto the swirler. And there you have a mode conversion process. So it converts the acoustic fluctuations into some hydrodynamic fluctuations, more particular into fluctuation of your swirl component. And this hydrodynamic perturbation is then traveling into the flame, again causing heat release fluctuations. So there's another coupling mechanism here. And then we have our helical global modes. Those modes do not directly cause a global heat release fluctuations as they are skew symmetric. However, as you will see, they also couple with the flame transfer function or the flame response, as you will see in this talk. And then finally, there's another mechanism, which I will just briefly mention here. It is the fuel-air ratio fluctuation. So what happens here is that typically the fuel is injected into the combustor somewhere near the swirler. And if you have an acoustic velocity fluctuation, at the point where you inject your fuel, you get a fluctuation of your fuel-air ratio, and these fuel packages are then traveled or transported into the flame, and then again causing heat release fluctuations. This last mechanism here is not directly related to hydrodynamic instability. However, these other methods, particularly Kelvin-Helmholtz type instability, of course, causes these strong rollers of vortices, and this affects the mixing of this fuel-air ratio fluctuation. So there's an indirect connection between these different mechanisms here. Okay, so this was the introductory block, and now we come to some results. We will first start with the Kelvin-Helmholtz type instability, and I already briefly tried to explain to you what the basic mechanism is. And now we're trying to model that mechanism. So what we did in the first step was we used local spatial stability analysis and used this to develop a low order model for our flame response. So how did we proceed here? We started to get some mean fields and mean density fields in our combustor. So in this case, we use PIV data, but this can also be done with numerical data, of course. And then we did a linearized analysis. So we used the spatial local analysis where we solve the local spatial eigenvalue problem with alpha here is my complex eigenvalue. And then we reconstructed our perturbation wave trend by integrating this complex eigenvalue in streamwise direction. And we get a gain and a phase lag. Okay, this is a very classic approach, I would say. And you get a gain distribution that is shown here on the top right side. So what this tells you is, it tells you how much the perturbation is amplified inside the combustion chamber when it is initiated at the position x equals 0. So x equals 0 is the inlet of my combustion chamber. So for instance, at 300 Hertz, we get a perturbation that is amplified by a factor of 1.5 approximately. And if we look into some data, so just to verify this model approximately or to make it plausible, you see here in the bottom some phase averaged PIV data, which was recorded simultaneously with some heat release measurements of the flame. So you see the roll-up of your Kelvin-Helmholtz mode, and you see how it is interacting with the flame, thereby causing heat release. Okay, so this is a coupling mechanism which is important here. And you can see that, okay, approximately your current structure is growing until a region somewhere here, and then it starts to decay. So this is approximately right what this local linear stability gives us. Then, of course, we still need to connect this result to get a flame transfer function or a flame response model. So we somehow need to connect this with the heat release. And we did here a very simple approach, but it actually worked quite well. We basically weight our complex eigenvalue, which contains the growth rate and the wave number of my perturbation, and we weight this with this intensity E, which is the mean intensity of our flame. And with this, you get a transfer function that relates the heat release to some velocity perturbation. And here you just see briefly a result. So the black dotted, the black symbols here are measurements of a flame transfer function, which was measured in this rig here, and the black line here is the prediction from our low order model here. And there are some details I can explain if you have questions afterwards. So the FTF, modeling the FTF is quite important, particularly for prediction of thermoacoustics. However, it is a black box approach, and we would also like to have some more information about the actual structure of the perturbation or the structure of the flow and flame response we have in our combustor. And second, the previous approach was based on a local spatial stability analysis, and of course this has some limitations if it comes to fully non-parallel swirling flows, and therefore we wanted to also use some global methods to continue in this area. And we used some resolvent analysis with the aim to recover the flow and flame response in our combustor. So once again, we took our mean fields here and we did a linearized analysis now based on the mass, momentum, and energy equations. And we conducted a global resolvent analysis where you get your optimal forcing and response modes and a specific gain. So here's the gain shown. So we get a very pronounced low rank characteristic. So the gain of the leading mode is much larger than all the other modes. So that is nice. And it also tells you already that there seems to be a hydrodynamic instability that dominates the response. So this is the Kelvin-Helmholtz type instability. And then we had a comparison of our optimal response modes with an acoustically forced response. So again, we had to do experiments, acoustically perturb our flame, and then record the flow and flame response using experimental methods. And here you see a comparison of the velocity fluctuations first. So on the top, you have the resolvent, on the bottom, you have your experiments. And you see that the match is actually quite reasonable for all the different frequencies we were looking at. And these frequencies are those frequencies which are important for thermoacoustic instabilities. And then we also made a comparison of our heat release. So since we are using the energy equation as well, we also have a fluctuating density field, and we can relate this fluctuating density field to the fluctuation of the heat release, which we recorded also in our experimental approach. We didn't expect this actually to work because the model is quite rough, just taking an energy equation here, but it seems to work reasonably well for these very low frequencies, while for high frequencies, it doesn't really work anymore. So what is missing here, most probably, is a reaction model, which we're currently trying to integrate so that we also get a good match for these higher frequencies. However, I think you can basically take two conclusions from this work. First, for low frequencies, your model here seems to work, and you not need to include any chemistry model to predict the flame response from a linearized analysis. And second, if we consider the flow response here, which seems to match for the entire frequency range, it seems like that the resolvent analysis, which represents the most optimal structures with respect to stochastic forcing, is quite similar to our flow response to acoustic perturbations. So this allows us to maybe determine the flow response and also the flame response from stochastically forced data and not needing to acoustically perturb our flow. So this may have some very interesting practical consequences. So basically, we're trying to reconstruct our flow and flame response from stochastically forced system, so from turbulent forced system. So here's the approach in a very simplified manner. We take some data in a combustor. So in this case, this was a collaboration with a company, and this is a full-scale combustor. And experiments are very difficult to do in this configuration. And we took some data, some OH chemiluminescence data and some PRV in such a combustor. And then we do a data-driven reconstruction of our response. So this is relatively straightforward. We did a spectral PUD on our velocity field. Then we did an extended SPUD to recover the heat release that is correlated to the velocity fluctuations. And then we compare this with acoustically forced phase average data. Okay, so the bottom line here is our ground truth, and the top row is our data-driven reconstruction. And you can see that the heat, and we're looking here at heat release in the combustion chamber, so heat release modes or coherent heat release, and you can see that there's quite a clear correspondence between the two. So this is actually quite nice because it gives you a possibility to determine a flame transfer function from naturally or stochastically forced data. And that is important for particularly running these very large scale rigs, because an acoustic forcing in such a rig is a very, very difficult task to do. Moreover, and this now gets a bit complicated, you can also do the following. You can then do a spectral PUD directly on your heat release, and then you can align your optimal modes you get from this approach with the optimal modes you get from your extended SPUD, and then you can plot an alignment metric as a function of frequency. And if you have high alignment, that means that most of the heat release response that is encountered in this combustor is driven by hydrodynamic instability. So this will give you some estimate of a frequency range where you actually know that the Kelvin-Helmholtz instability is the dominant driver of the heat release. While in other areas where you have a low alignment, you know that there's some other mechanism relevant. For instance, the fuel-air ratio fluctuations, which I explained at the beginning. All right, so this was the Kelvin-Hamilton instabilities, and now we're going further to the inertial waves or swirl fluctuations. And as I explained at the beginning, these fluctuations occur as an acoustic wave is impinging on our swirler, and that causes a mode conversion process and generates hydrodynamic fluctuations, typically in the swirl component, which is then traveling downstream into the flame. And one important information that is currently under debate is how fast do these swirl fluctuations travel as they go into the flame, because it's really important to get this information right, because it determines the time delays you have in your system, and therefore it determines the way how you and therefore it determines the accuracy of your thermoacoustic instability prediction. Okay, so we are basically mostly interested in determining the velocity of these fluctuations, the transport velocities. But first, we need to know whether these flare fluctuations are actually associated with inertial waves, because this idea is an idea that just arose 2 years ago, maybe, and we were trying now to see if this is actually the case for fully turbulent flow. So what we did first was we did an experiment to demonstrate the existence of inertial waves in turbulent swirl combustors. So here's a sketch of the experiment. We have here a swirler, and downstream of the swirler we have a mixing section. And in that mixing section we did some PIV measurements. And from this based on these PIV measurements, we did a spectral POD analysis, and we identified a reasonably strong low rank behavior. So that already gives you some indication that there seems to be some amplification mechanism happening in that regime here, in that data. And the leading SPOD mode is shown here on the right side, and it shows a structure with relatively long wavelengths and some very high fluctuation amplitudes at the jet center line. And then we compared these modes. Here are profiles shown of this mode. So the axial and azimuthal velocity component of that mode here at a given streamwise position. And we compared these profiles with the analytic prediction of Albarak and co-workers, so researchers at the TU Munich, who and Matthew Juniper and Wolfgang Polifke were the three, I believe. They predicted these inertial waves based on a very simplified velocity profile, just a solid body rotation with some plug flow, and did a linear stability analysis and determined an analytic solution here. And this is shown here in blue, and you can see a very nice match here. So that basically already gave some good experimental evidence or proof that we do have inertial waves in such a combustor. However, so far we only know that the response of this flow field to stochastic forcing is featuring these inertial waves. But we are of course also interested in modeling the forced response. And we were asking ourselves, is the forced response we get in such a mixing duct also related to inertial waves? And for this, we had to do first, of course, measurements of the flow response to acoustic forcing. This is shown here in the bottom. So our PAV domain doesn't reach really far up into the swirler. So there's a bit of regime where we don't have any information. And then downstream in the mixing duct, we get this wavy structure. So this is basically the response of our flow to the acoustic forcing. And then what we did next was we did a resolvent analysis on a simplified base flow. So we basically took the same base flow as our co-workers at TU Munich, so a solid body rotation and a plug flow, and did a global resolvent analysis based on this base flow. And we get some structures that already look quite similar to what we find in our experiment. So with this wavy structure here on the jet center line. So actually this already tells us that yes, inertial waves, which are the only one that can exist in such a simplified base flow, are actually responsible for this type of response. Then we did an LEF study because we wanted to have now the realistic base flow and not the simplified base flow. And we did a resolvent analysis on this realistic base flow. So here on the left, you see the LES results. So these are the mean fields on which we did our stability analysis. And here in the middle, you see the most optimal response we get here. And you can see that now we are even catching some of the structures that are more in the outside. So we get a really decent comparison with our experiments. And as I said at the beginning, the transport velocity of these modes is very important for thermoacoustics. So what we also try to do is we work out the streamwise phase velocity of these modes as a function of frequency. Now we sweep through a wide range of frequencies, and the black symbols here are the experimental data coming from the PIV, and the colored symbols here are the predictions from the resolvent analysis. And as you can see, the phase velocity is reasonably well predicted for a wide range of frequencies, but for low frequencies, we do have some scatter of the data, and this seems to be related to the type of closure model that we're using. So there needs to be some further investigations here. Okay, that was it regarding the inertial waves, and I come now to the last topic, which are the helical global modes. So basically, the most dominant global mode you find in the swirling flow and ongoing vortex breakdown is a single helical global mode. So this is a very established information right now. And our question was, how does this global mode affect the combustion process in general? And today I'm going to talk about its effect on thermoacoustics in particular. And here we have the following problem, that at least in an experimental arrangement, you cannot really control the amplitude of that oscillation, since it's a self-excited oscillation. So you need to have some tool in order to suppress that instability to see its direct impact on the combustion process. And therefore, we were trying to develop an active flow control method that allows us to control that instability, okay? And how we proceeded here was that we first had to understand the natural instability. So we did some PAV measurements in a combustor, and then we took the mean field. So this is now actually not a combustor flow field, it's a generic swirling flow configuration. So this is more like a fundamental study and not directly done in a combustion chamber. And then we did a global stability analysis of this flow. And we compared our results with our experimental data. So you can compare the frequency you get. So your limit cycle frequency of your instability, you can compare to the eigenmode you get in your linearized analysis. And then you can also compare the eigenmode, and you get, in this case, a very good comparison. And then, of course, you can look at the structural sensitivity to work out the wave maker region of the flow, and you can see, okay, it is located somewhere upstream of the stagnation point. This is not directly surprising, but it is relatively different to some results that are available in literature related to laminar swirling flows, where often the wave maker is located rather in the bubble or even downstream of the bubble, okay? And then also the receptivity to open loop forcing can be determined from the adjoint of the eigenmode. And you see that there's a strong receptivity upstream of the bubble in the mixing duct, okay? And this is very important for us for flow control studies, because it might tell us where to place an actuator to get an efficient control of this global mode. So we also tried to find out whether this receptivity is, let's say, reliable. And we therefore first did some open loop experiments where we actuated and where we placed an actuator at different streamwise positions here in this mixing duct, and we did some lock-in experiments. So we were asking ourselves, at what position do you need the least amplitude of actuation to get a lock-in of your natural oscillation onto the actuator, okay? And you can see that there are some responsive and non-responsive in this area. So non-responsive means you need high amplitudes in order to achieve lock-in. And you could find quite a good correspondence between this receptivity maps here and the actuation lock-in experiments. So then we used this information to design an active flow control device, which we implemented into a combustion rig. So this is basically a center body, or it's basically consists of 4 loudspeakers, which are connected to 4 tubes, and these tubes are guided into a center body, which is located in the mixing section. And at the end of the center body, you have 4 azimuthal jets that you can inject at different phase locations so that you can do a M=1 perturbation. And I'll just give you a few results which I find quite interesting. So what we did next was we verified our control scheme by doing again a stability analysis of our uncontrolled flow case. So now we're in the combustion chamber, we have a flame, so it's a reacting flow. And what typically happens in a combustion chamber is that when the flame anchors to a center body, it suppresses the natural instability. So the global mode is actually suppressed, and this can be also seen here in the stability analysis. So we find an eigenmode that is stable, and this eigenmode represents our M=1 instability. What we did then was we did a parametric study where we run our actuator at different frequencies and different amplitudes. So this mu here is a momentum coefficient. It relates the momentum of our actuator to the momentum of the mean flow field. So you see these amplitudes are very, very low. And we sweep through these frequencies, and we were asking ourselves at what frequency we have the maximum response of our M=1 oscillation. And we quantified this by the heat release, but this is a detail now. But what you can see is that we have the maximum response of our flow and flame dynamics at the frequency where we have our slightly damped global instability. So this is a nice correspondence here. So it tells us that our actuation of our global mode is actually working quite well. And you can also see in the response of the velocity that we measured in the combustion chamber that it looks quite similar to what our stability analysis is showing us. So then we used the control scheme to see if we have any effect on the thermoacoustic oscillations. And this was our one of the first results we got. So we run the combustor now at an unstable condition. So we run into an operating condition where we have strong pressure oscillations due to thermoacoustics. And then we turned our actuator on. And as you can see, as we increase our actuation amplitude, we get a strong suppression of our thermoacoustic amplitude here. So we could definitely see a very strong way of controlling the thermoacoustic through an actuation of our global mode. And the explanation for the mechanism that is responsible is quite involved here, but I will try to make it really short. So basically what happens is, as you actuate your global mode, you start to thickening your shear layer and you reduce the gain of your Kelvin-Helmholtz type instability, which is shown here. This result is from a local stability analysis based on the controlled flow states. And this reduction of gain of the KH instability then reduces the gain of your flame response, and that then stabilizes the thermoacoustic oscillations. So in simple words, you excite a global mode that corrects the mean field as such that you have a suppression of your KH instability, which then reduces the coupling with heat release and suppresses your thermoacoustic oscillation. So although there is no direct effect of our global mode to the thermoacoustic, there is an indirect effect via the mean field. So I'm almost coming to the end of this seminar here, and I will just briefly show you a few results which we have, which we got quite recently and which we're still working on. So this is pretty much work in progress, and I'm not even sure if it's going to be so relevant, but I find it quite interesting. And this is about the interaction of multiple global modes. So what we basically considered here was a swirling flow with a two-fluid interface. Okay, so this is not directly related to combustion, it's more related to hydro turbine applications. And we did a nonlinear simulation of a laminar swirling flow here. And what we found was that at a certain critical swirl number, we get a bifurcation of our flow state into an oscillating state. However, this oscillation was governed by two frequencies. And these two frequencies, so the higher frequency here in blue was double the first frequency. And the red frequency, the first frequency was associated with a single helical structure, and the second frequency with a double helical structure. So, I mean, that looks pretty much like a triadic interaction or higher harmonic interaction between the first and the second frequency here, and maybe not so surprising, except for the fact that the second frequency is so much higher than the first one. This is not something we would have expected. If you increase the swirl number, so you go a little bit further with a little higher swirl number, you then additional peaks appear in your dynamics, which shows you some triadic interaction between these different frequency components here. Looks more or less what you would expect. However, what made us quite surprised is that if you do a linearized analysis of this flow state, so here what we did was linearizing a DNS code and then running a DMD on our linearized time stepping solution, and worked out the growth rates and frequencies of these linear modes. And basically what you see is that these two frequencies are both associated each with a individual linearly global mode. Okay, and these global modes actually become unstable at the exact same operating conditions and with exact same growth rates for a certain amount of, or within a certain range of operating conditions. So apparently what you have here, you have an interaction of two linearly unstable global modes, and this interaction is so strong as they are aligned to each other, or the M=2 mode has exactly the same shape as the higher harmonic of the M=1 mode. Okay, so there is a very simple path of nonlinear interaction. Well, this is a quite funny result maybe, but I would also like to demonstrate that this might be even relevant for more complex flow systems. So what we have here are results from a study we do with Rolls-Royce, a gas turbine manufacturer, and we analyzed some LES data of a Rolls-Royce engine. And this is a very complex flow configuration with a dual swirl combustor. And in the nonlinear simulation, we find very strong peaks. Okay, so the spectrum shows here some very discrete peaks in the reacting as well as the non-reacting cases. And we did a linearized analysis or global mode analysis of this case. And we could actually find for each of these peaks, we could find a corresponding global mode. And the shape of the global mode corresponds also very nicely with the shape of these response, or with the modes associated with this peak. So again, we find here a strong interaction between several global modes with different azimuthal wave numbers, and these modes are again aligned in frequency space, aligned to each other, as such to have a very strong interaction. And one question that puzzles us a little bit is, how is it possible that these modes actually align in multiple frequencies to each other? And my current understanding is that it is because we have the following. We have here in the bottom, we see the structural sensitivity of our global modes, and we see that all these azimuthal modes have the same region where they are basically selected. In that region, you have the frequency selected of the global mode. And in that region, you have the same swirl velocity, and the swirl velocity determines to a large extent the frequency of your mode. So basically this explains or gives some plausibility to these results, that with higher azimuthal wave numbers, you get always the multiple frequencies. All right, so this brings me to the end of my talk. The conclusions, I don't know. I mean, I think, I hope I could convince you that swirling flows are a fascinating topic to work with, and that hydrodynamic instabilities play a key role here in thermoacoustics, and that mean field stability theory is very suitable to analyze this and also to do some prediction and control. And it allows for a better interpretation of the numerical and experimental results. So it enriches the discussion, I think, very much, which I really like. And I just put here some outlooks. So what we are trying to do in the future, we also focus on closure problems for reacting flows. We want to use round-based data assimilation and a joint-based optimization. Yeah, so I just would like to acknowledge my co-workers in my group and also my funding schemes. I'm very happy to work with these very, very talented researchers, and thank you for your attention and happy to answer some questions.
Great. Thank you so much, Kilian. That was an excellent talk, and you've definitely convinced me that swirling flows are fascinating. So we do have some time now for questions from the audience. Feel free to unmute and ask away, or raise hands, also fine. So we already have one hand raised. Sai Daba, perhaps you'd like to start.
Hello, Professor Kilian. This was a really interesting talk. I'm actually a PhD student at Monash, and we are working on like swirl-induced cavitation in fuel injector nozzle. And I was hoping you could give some insights on how you created the experiment to get the solid body rotation with the plug flow.
Okay. I mean, that's, if you really need to have a plug flow, then you cannot use a contraction. Okay. As soon as you have a contraction. So what my first slide I showed, where you have this rotating honeycomb and then you have a contraction downstream, that contraction will always generate you a hump of your velocity profile. If you don't mind about this, then this is the way to go. If you don't want to have that hump, then you cannot have a contraction, and then you don't have a top head velocity profile of your axial. So neither of these possibilities are very satisfactory. So there's a paper from Liang and Maxworthy very long ago who used a rotating honeycomb and a rotating nozzle to generate something that is kind of comes very close to really a top head profile and a solid body rotation, because then you also don't have this shear layer, this azimuthal shear layer. You don't generate that shear layer in your contraction as well, because you don't have a boundary layer, an azimuthal boundary layer. So, but it's really complicated. You need to have a rotating contraction. So basically you have to rotate almost your entire rig. So other than that, we played a lot with different types of swirlers, and you will never, I think you will never get something that is very generic. So at the end, I think you have to give up the idea to have a generic swirling flow, like you have a generic non-swirling jet, which is a top hat and nothing else. So this, I believe, is not really possible in a swirling flow. It's always case dependent. So I don't want to talk too long now about this topic, but the size of your vortex core, the size, the radial extent of the region where you have solid body rotation already determines quite a lot about the dynamics you have. And this size depends very much on your facility. So at the end, you need to document your facility properly and then describe what you have, but you won't get a very generic situation.
Okay, thanks. And again, thanks for an interesting talk.
Welcome.
Thank you. So we have another question. Tushar, go ahead.
Hello, Professor Kilian. This is Tushar. I'm a PhD student in University of Melbourne and working jointly with LTRAC Monash under Professor Julio Soria. So it's a very interesting talk and I really liked it. I just had a small question from your initial part when you were explaining the various thermoacoustic instability modes, and you showed a video having simultaneous PIV as well as heat release rate measurements. So just curious about those heat release measurements. Was it a point measurement or a field measurement, like something?
We use intensified OH star cameras. So basically you use a normal camera or a high-speed camera. You use an OH filter and then a light intensifier. And then you record your data, you take a phase average of that data, and then you do a tomographic reconstruction of your heat release. Because you have line of sight information, then you need to reconstruct the planar view of that heat release by assuming a symmetry of your phase average data, and then you get what you saw.
Okay. Yeah. Thank you so much. And I assume like both the PIV as well as your OH intensified camera would be triggered simultaneously to ensure.
Yes, exactly.
Okay.
They were the same cameras and they were triggered with the same trigger. And yeah, you have to be careful that the timing is right, but it's exactly what we did. Yeah.
Yeah. Thank you so much.
You're welcome.
So we have another question with a raised hand. Vishal, if you'd like to unmute.
Hi, Professor Kilian. I was just wondering, when you have a mean field correction because of using the actuator, does it actually change the swirl number? When is the swirl number changing?
That's a good point. So I need to remember. We gave some explanation in the work. I said so, not exactly in this situation where you're referring to, but a few slides before I was showing these lock-in experiments. And there we were looking a bit more detailed into how this lock-in actually works. And in one situation, you could show that by changing the mean field through the actuation, you actually affect the swirl number exactly, and that changes the frequency of your natural oscillation. That is actually the mechanism that leads to lock-in. So generally, yes, this can happen. Specifically, I don't know if it happened in the case I was talking about, where I was looking for the Kelvin-Helmholtz step instability.
Oh, okay. That's what I was wondering. That, yeah, because it should change, right? I mean, because the whole mean field is being corrected. Yeah. All right.
Yeah, I mean, it can change. It should. I don't know. I mean, it depends. I mean, you could. As far as I remember, it was depending on the type of. I need to have a look at the paper. So I would suggest you to look at Jens Müller's paper, JFM paper, and in 2 years ago, and he showed the swirl number as a function of actuation frequency. And I don't really remember if it always changed or if it only changed in a certain regime. So but in generally, yes, but in specific, I wouldn't say that it always has to. But why not? You're right. Why not?
No worries. Thanks. I'll have a look at the paper. Thank you.
Thank you.
Okay. Any other questions coming from the audience? I might just ask a quick question. So you did talk briefly about having your eddy viscosity and your diffusivity. Like I think you said you calibrated them to the data. This was quite early on. And so is there a way that you could calculate them like kind of a priori, or is that when you said in future plans, like thinking about RANs and those type of models, is that where that might come in?
I mean, of course, if you're using a RAN simulation right from the beginning to get your base flows, then you could take the eddy viscosity you get from your RAN simulations. But we do not want to rely on the solution of a RAN solver because it often fails. And but what we want to do is we want to assimilate a RAN solution onto the mean fields we got from accurate mean field and prediction. Let's say LES or experiments. We want to assimilate a RAN solution with a simple eddy viscosity model onto the data, and then we take this eddy viscosity for our linearized analysis. And then what you can also do, I mean, this is practically sometimes useful or not. You can use very simple eddy viscosity models that are, so you relate your eddy viscosity to a characteristic length scale and a characteristic velocity, and you can take this. So in some cases, like in what Phoebe Kuhn was doing, she has a paper just recently published about the Coherent structures in the far field of a jet, and there the eddy viscosity models are very reliable and simple, and you basically just take characteristic velocities of your mean field and characteristic length scales, and you already get a good approximation of your eddy viscosity. So in some cases, you can get it directly from the mean field, but these are the very rare occasions.
Understood. Yeah, it's such a rich problem, definitely.
Yeah, but I want just to say that it is, in my opinion, this is just an opinion based on experience, it is less of a problem, I would say, than you have when you do run simulations. So the closure problem definitely is important, but the type of model that you're using is less important than it would be, for instance, if you try to close the runs equations for nonlinear simulations, because you base your analysis on the mean field, and that already has so much information about your nonlinearity that the actual closure model is important, but it's not game changing, I would say.
Yeah, that's an excellent point, I think. All right. Before we finish up, are there any other questions coming from the audience? Otherwise, oh, we've got some applause coming from the audience, but otherwise we might finish up for this week. So thank you again, Kilian, for your excellent talk. It was a pleasure having you in our series, and hopefully I'll see most of you people in the audience next week. See you later.
Thank you.
Thanks.